Before we get into a discussion on how limits are calculated in ERA, we have to have a basic conversation about what combined loading is and what actually happens to the pipe when we do different things to it in the wellbore. So this is a short PowerPoint presentation that discusses some basics of tubular mechanics. And this is just a good background refresher for most engineers, and for those of you that don't have a background in engineering, it's some interesting information. So this all kind of starts with the classic stress-strain diagram. And so what we're looking at here is a classic stress-strain curve for a test of a sample of API L80 grade casing. And on the x-axis, what you're looking at is strain, which is the percentage elongation. How much longer did this test sample get as we started to apply load? Starting from 0% to 2.5%, which arguably is pretty small strain. And then along the y-axis, we've got the stress. And of course, the stress is just the load and the divided by the cross-sectional area. And that's how we arrive at units of pounds per square inch. Something that is kind of interesting here is in the early region of this curve, with very little strain, up to about 70,000 psi of stress, we remain within what's called the elastic region. And basic mechanics and materials states that when your material is behaving elastically, when you apply a load to it, as soon as you take that load off, the material returns to its original shape, similar to what happens when you pull on a rubber band. If you've got a 5-inch rubber band and you stretch it out to 10 inches, when you take your finger off of one end of the rubber band, it snaps back to 5 inches long. And that's what happens with our drill pipe in this case, or our casing in this case, is when we're applying load that's below 70,000 psi of stress, it'll return back to its original shape. It's behaving elastically. Now, at any load above this point, we enter into the plastic region. And once we get into the plastic region, the material doesn't return to its original shape. There's also a phenomenon that happens in this region called cold working, and we'll get into why we don't really want to cold work our drill pipe or tubing or casing when we're executing well operations. So those are the two basic regions, the elastic region and plastic region. Now, there's also some key points on this curve that are important to know, and the first one is what's referred to as the proportional limit. And the proportional limit happens to be that point that we cross over from the elastic region into the plastic region. Beyond that point, we're no longer behaving elastically. Now, at 0.5% strain, depending on the grade of the material, what API says is at 0.5% strain, we've reached the yield strength. So when somebody talks about the strength of the material, what they typically mean is the minimum yield strength. What is the specification in API that says your material needs to at least be this strong? So here in this case, this would be an 80,000 psi material, or L80 grade. Notice that just because we're saying that that's the minimum yield, the pipe has actually already yielded at that point. In fact, we've permanently deformed the pipe. We've got into the plastic region down here at 70,000 psi. It's not a lot of plastic working, but there is some. There's not a lot of strain, so it's just at the beginning of that cold working process. Now, the ultimate strength, or what's also sometimes referred to as the tensile or tension strength, is much higher, and this occurs way out here at around 2.25% strain, or a little over 90,000 psi of stress. That's the point where the pipe fails, and you can see very quickly the stress starts to fall off because we're now pulling the pipe into two pieces. Notice that the ultimate strength is quite a bit higher than the yield strength, and also quite a bit higher than the proportional limit. So when we say that we have put a certain amount of stress on the pipe, just because it's right at the yield strength, that doesn't necessarily mean the pipe's going to break. It means that it will certainly deform plastically, but it doesn't break until we get out to this point. Something also that's interesting is the slope of this initial line when we're behaving elastically up until the proportional limit. The slope of this line is what's referred to as the modulus of elasticity, or Young's modulus. And that slope is really, you could think of it as a stretchiness factor. And that Young's modulus or slope is also how we will calculate stretch in a drill string. So what falls out of this? Hooke's law, or Hooke's equation, the stretch equation, says that the strain for a particular object is going to be equal to Young's modulus, what's referred to as often symbolized as the letter E, modulus of elasticity, divided by the stress, that stress symbol sigma. That's basically your stretch equation. If you want to figure out stretch in the drill pipe or stretch in the casing, that's the equation you'd use. Poisson's ratio, or what I prefer to call the squishability factor, is simply the radial strain divided by the axial strain. And this negative symbol is an indication that what we're talking about is the radius of the pipe getting smaller. How much smaller did it get as we started to apply a positive tensile load? And the opposite would happen if we applied a compressive load. The string would get shorter, so the strain would be negative and the pipe would get fatter, and the radial strain would be positive. So those are some interesting little facts about the stress strain curve and how we use them in engineering. Why is that important? Well, before we get into that, we need to give you a little bit of background about API pipe. And what you've got is a list here of different API casing and drill pipe grades. The drill pipe grades are in bold, so E75, X95, G105, S135. And what API says the absolute minimum yield needs to be and what the maximum yield strength needs to be. And then also a specification for the absolute minimum that the tensile strength needs to be. So you notice that there's a range here. If I have S135 drill pipe, the minimum yield strength could be anywhere between 135,000 and 165,000 psi. So this point right here could be as low as 135 or as high as 165. So that's quite a wide window that the drill pipe manufacturer has to hit. Any particular joint could be in that range. Well, this is a kind of an interesting piece of data. This was a 700 test sample set from a casing manufacturer where they took some L80 pipe and they performed that stress strain analysis to figure out what the yield strength was and did some statistics on it. And you can also see with the red vertical lines what API specifies as the minimum yield strength and the maximum yield strength. And for the most part, most of those sample tests fall within that range. But there's a few tests that fall below the range and a few tests that fall above the range. But the vast majority of the data is somewhere in that range. So it's real important when you're thinking about what you're doing to the pipe is just how strong is the pipe, how confident are we of its strength. And what this graph tells me is that any given pipe can have a pretty wide range of strength. Just because we look into API RP7G or we look into THL's DS1 catalog and we look up the strength of the pipe, know that what's going into that is this line right here. When we're talking about the strength of the material, we're assuming that the pipe is this line. Well, it's probably stronger than that. But we have to assume something. So we assume that the minimum strength is along this line. All right, so what does that mean to the way that we design our wells and the way that we operate in our wells? K&M has a philosophy where we say that we're always going to do everything we can to make sure that we stay in the elastic range. If we get outside the elastic range, we could potentially permanently deform the pipe. And permanently deforming the pipe doesn't necessarily mean that we're going to have a failure at that point, but because we start cold working the material, we run the risk of cold working it and changing its inherent properties, particularly the ductility and the hardness. And if we start doing those things under certain well conditions, we could lead to a fatigue failure or corrosion failure later on down the road. And that's certainly not something that we want. So to avoid that risk, we say we're always going to operate in the elastic range. In our software, what we assume is that we're going to operate with a design factor of 1.2 in terms of the total stress in the pipe. Later on, we're going to talk about what VME stress is. That's total stress. We say that we don't want to operate in excess of that 1.2 limit, meaning that if we have a yield strength of 100,000 psi, we're going to derate that by a factor of 1.2. And if you think about it, that kind of covers our basis, because if we did have some material with a yield strength of 80,000 psi, we really need to operate down here below 70,000 psi if we're going to stay in the elastic range. So the basis of that 1.2 might sound very conservative, but it's only conservative if our actual strength happens to fall out here in this range. And it probably will, but we know that the safer assumption would be that we're somewhere in the minimum yield strength, which API specifies. And just as an aside, if you were operating with a design factor of 1.0, it doesn't necessarily mean that the pipe's going to break. Because of those statistics I just showed you, it probably isn't going to break at a factor of 1.0. Really don't know what the strength is anyway, but immediate failure, pulling the pipe apart, isn't guaranteed unless our load exceeds the ultimate strength. And of course, the ultimate strength for L80 grade pipe is way out to 95,000 psi. So let's move on to what actually happens to pipe when we drill a well. Well, there's various things that we can do to it. We can pull it apart, which creates a positive axial stress, and the engineering symbol for that tends to be sigma, lowercase a. We could crush the pipe. We could put it in compression, so that's a negative axial stress, also sigma, lowercase a, just sign convention here, whether we're positive or negative. We could bend it around a curve, which essentially is an axial stress, but for a couple of reasons that I'll get into later, we treat that a little bit differently. But bending stress, when we bend pipe around a curve, it creates some positive axial stress on the outside of the curve and some negative axial stress on the inside of the curve. Normally, we treat this bending stress with sigma b. We could also twist the pipe. When we put torque in the string, that creates a shear stress, and that is treated with this Greek symbol tau. We try to blow the pipe up by putting a whole bunch of pressure on the inside. Pressure on the inside, no pressure on the outside. That creates positive radial stress, sigma r, and it creates a positive hoop stress, and that's sigma with theta. Now we could collapse it. What I mean by collapse is put pressure on the outside and have lower pressure on the inside. That creates negative radial stress, and it creates negative hoop stress. The other thing we do to the pipe that doesn't in itself necessarily cause the pipe to fail, but indirectly, heating and cooling the pipe can cause changes. And in particular, when we get the pipe real hot, that tends to reduce its tensile strength, reduce its minimum yield strength, and it also changes the modulus of elasticity. Depending on the material, those changes can be significant or they can be relatively minor. So axial stress. Axial stress, just simply the load times the cross-sectional area of the pipe. Pretty simple equations. The sign convention is positive for tension, negative for compression. And those are the basic equations that we use. Bending stress, of course, wherever you have a dog leg, pipe has to go around that dog leg. So as it goes around this curve, these fibers of the pipe get compressed and these fibers on this side of the pipe get stretched. So there is a change to the axial tension in the string on this side versus this side. This is also a phenomenon that creates a cyclical stress when we start rotating the pipe. And what I mean by that is this fiber in the pipe right now is in tension, but if we were to rotate it 180 degrees, all of a sudden it would find itself over here on this side, and now it's being compressed. So as we rotate, those fibers are getting flexed back and forth, back and forth, back and forth like a paper clip. And that can ultimately lead to fatigue, which we'll cover in a separate section. But for now, bending stress, simple pure bending around a curve, is calculated by taking the Young's modulus times the radius of interest, which really means how far from the center of the pipe to the point on the tubular that we want to analyze. The radius would be from the inside to the ID surface, if we're interested in that point on the pipe, or from the inside to the outside surface of the pipe if we're interested in that point. So that's what we mean by radius of interest. We multiply that times the dogleg severity in degrees per 100 foot, multiplied times pi, and then we divide by 216,000. And these are just for oil field units. That pressure in PSI, or stress, is added or subtracted from the axial stress that we arrived at over here. It turns out that bending is actually more complicated than what I've just shown here, and I don't want to get into too much detail, but the basics of it are there is an amplification to the bending stress whenever we start to apply tension around a curve. And we'll cover that a little bit later on, but just basic fundamental bending, this is the equation that we can use. Tension doesn't come into play. We just add or subtract this to the tensile axial stress that we calculated in the previous slide. Now, the shear stress or torque stress for us drillers is also pretty easy to calculate. The torque stress is 12 times the torque in foot-pounds multiplied times the radius of interest. Again, are we talking about the ID surface or the OD surface? Divided by the polar moment of inertia. And polar moment of inertia is just pi over 32 times d to the fourth power minus little d to the fourth power. Of course, the big D is OD, but little d is ID. Real easy to calculate torque stress. Inside pressure. So when we put pressure on the inside, that's going to create a positive hoop stress and a positive radial stress. The radial stress on the inside is this big old long equation with some pretty simple components. And then the hoop stress on the inside is calculated with this equation. Very similar, but a few minor little differences. The radial stress on the ID turns out to just be your internal pressure. So if you have 5,000 psi on the inside of the pipe, that works out to 5,000 psi radial stress. Now, outside pressure, a little bit different effect here. We're trying to collapse the pipe as opposed to burst the pipe. And these are the equations that we use for figuring out the radial stress on the outside and the hoop stress on the outside. The one caveat here is these equations don't necessarily tell you what your collapse load is. Collapse is a little bit more complicated. It turns out that collapse is more of a stability problem than it is a yield problem. It just depends on the dimensions, how big the pipe is and how thick the wall thickness is. So API actually came up with 4 different formulas for calculating the collapse strength of pipe depending on different phenomena, whether it's yielding, which is what we've been talking about here with the stress strain diagram, or is it some plastic deformation, is it transitional, or is it elastic? And without getting into a lot of distraction, if you're interested, just send me an email and I can send you documentation on how those things are calculated. But if you're truly trying to figure out if pipe collapses, we don't apply these equations necessarily. So what does all this mean? Combined loading. When you have a tubular in the hole and you're doing lots of different stuff to it, if you got pressure on the inside and you're putting torque on it and you're pulling on it and you're putting it around a curve, how do we know if all the combination of things that we're doing is going to break the pipe or not? Well, there was this guy back in the 1900s, Richard von Mises. He was an Austrian mathematician, and he came up with this way of taking load in all different directions and trying to rationalize it into one, what he calls equivalent direction. And by equivalent, we're saying, well, you know, I'm turning the pipe here and I'm pulling on the pipe here. What's the combined effect? Well, the von Mises equivalent is how we take load in all these different directions, different axes, and figure out if we're going to yield or deform the material. And this is commonly used in casing design. What we've got here is a little graphic of what's referred to as the VME ellipse for a biaxial load. Biaxial meaning 2 different directions. I could load the pipe in tension or compression. So to the right of 0 is when I have a tensile load on the pipe. To the left of 0 is when there's a compressive load. And then you can also see on the y-axis we've got positive pressure on the inside, which is burst, or negative, being collapse. And then this blue ellipse represents the VME condition. This is the yield strength of the material as it goes under different combinations of load. And then this red area is that ellipse with a design factor applied, probably a design factor of 1.2 or 1.25, I would guess. Yeah, probably 1.25. And then overlaid on top of that is this box. And the box represents just the pure API ratings for this pipe. So the burst rating for this pipe is this horizontal line. The API equations say, you know, it really doesn't matter if you're in tension or compression. This is the burst load on the pipe. And then this would be the compression rating of the pipe. Over here we'd have the tension rating in the pipe. And then the green curve would be the collapse rating of the pipe. And really what we always try to do in casing design is operate in the smallest enclosed area when you combine this box and this red curve. We're trying to stay within a safe region, which would be the smallest area. It would be this curve here, this edge of the box, and then we'd come down to where it touches the red curve here, and we'd swing along, and then we'd meet up back at this corner. Anyway, this isn't supposed to be a conversation about casing design. It's just a little bit of background on what VME is. What is the limitation of VME? Well, it works well with ductile materials, but when we get into brittle materials, it doesn't work as well. Fortunately, we're not normally working with real brittle materials for most of our wells. The other time that VME by itself doesn't work very well is when collapse is a primary failure mode. If we were loading up a lot of pressure on the outside and not much pressure on the inside, you notice that this red curve, that's the VME limit condition, and the pipe actually collapses up here where this green curve is. So we wouldn't want to trust the output of this VME calculation if collapse was our primary concern. So it's just something we need to double check. But under other conditions, it's perfectly valid to honor this VME condition. So combined loading, what are we doing? Well, we're looking at a little piece of pipe, a little segment or section of pipe, and combining hoop stress, radial stress, axial stress, bending stress, and shear stress. And this is how the equation works. The VME equivalent is equal to the square root of the radial stress squared plus the hoop stress squared plus the axial stress squared. And of course, this Z, when we use the notation Z, that's what we mean is effective axial stress, which is my axial stress plus bending, minus radial times hoop, minus radial times effective axial, minus hoop times effective axial, and then we add 3 times my shear squared. And that will produce a value in units of PSI. What we try to do is operate at less VME stress than the yield strength of material if we want to stay within that elastic region. Now, it's important to evaluate the VME on 4 different surfaces. The outside of a curve, so when we're curving pipe around a dog leg, let me just zoom back to this little diagram. The outside of the curve would be this edge, and of course on that outside curve I've got the OD surface of the pipe and the ID surface of the pipe. I need to evaluate both of those places. And then of course on the inside edge of the curve I need to evaluate the OD surface and the ID surface. So when we talk about VME, we're evaluating it 4 times. And what we plot in our software is the maximum or the worst case of each one of these. And on any given well, under certain circumstances, some of these are going to be worse than others, depending on whether or not the pipe's in compression going around a curve or is the pipe in tension going around a curve. But what we plot is the worst one. Now, I mentioned earlier that temperature has an effect. Heating the pipe reduces the strength and the Young's modulus. At 300 degrees Fahrenheit, standard steel drill pipe is 7% lower strength than what it would be under ambient conditions. We don't drill too many wells that are really, really hot, but once we start getting up into that territory of 300, 400 degrees, it's important to take this into account, especially if we use more exotic materials, like if we were to use aluminum or titanium. They're more dramatically impacted by temperature changes, and that impact is not a linear equation. It's a linear equation for steel and a linear equation for titanium, but aluminum behaves a lot differently. And here I've got a few examples. What this table shows me is how much lower the minimum yield strength is compared to ambient conditions at 70 degrees Fahrenheit when I heat the pipe up to 100 degrees. You can see at 100 degrees Fahrenheit, the strength is only 1% lower, pretty insignificant. At 200 degrees Fahrenheit, for steel, it's 4% weaker. For titanium, it's 5% weaker. Aluminum, group 2, and so there's 4 different groupings of aluminum alloys in ISO 10400, which classifies these materials. Certain groups of aluminum are over 10% weaker when we're at just only 200 degrees Fahrenheit. And as you move on up the scale and we get into hotter and hotter wells, at 400 degrees, you can see that we're seeing some pretty substantial strength reductions. Look at this aluminum group 4. It's 40%, almost half its strength when you get it that hot. Now, of course, this table is graphically represented over here on the right, and you can see that some of these alloys have some pretty abrupt changes when we get them very hot. Those are all things that we account for in our software. It's not implemented just yet in ERA, but in the very near future, this will also be included. So what we'll do versus depth is reflect the impact of the strength degradation under applied temperature. So I hope you enjoyed that. That's just some important background information on tubular mechanics.